Let's also take the motion of our packed debris and take that velocity to apply it to the smoke values as well. Now in this situation, it's not a good idea to use a collision velocity like I just showed you, because these pieces are really small and it's not going to mesh with enough resolution. And if you tried to do that, it would just bog everything down and not really work. So in this situation, if you want to take the motion of points and create a custom velocity field, here's how you would do that. I've merged in the debris right here. I'm going to delete the geo, but keep the points. While we're at it, let's also clean this up. So we just have points, and we want to even delete the velocity on these points because it's better to just use a trail SOP and calculate velocity right here. It'll give you a more accurate result. Okay, so compute velocity right there. And before we compute that, let's also delete every other point. We don't need this many points when we're doing this. So yet again, let's do a group by range right here. And let's just delete half the points. So select one of two. And we're going to call this group here delete points. And then we'll use a blast to blast that away. So points, delete points, and let's also change this to points right here. Okay, so we've deleted half the points. Let's actually go a bit further with that. Maybe 1 out of every 3 stay selected, delete non-selected. We're now down to 33,000. Now don't mind the extra pieces showing up right here. If we just hide other objects, we only have the points. Middle mouse, 33,000. There's multiple ways of going about this, so I'm going to show you 2 separate methods you could use. The first one uses a node called velocity volume, or volume velocity. It takes the points, it takes a traditional volume, so if we use just the regular old volume node right there, and it basically fills this volume with the velocity on these points. So on this volume, let's start off by specifying this as a vector volume. We'll call this our debris vel. Our initial value is 0. Again, we don't want any velocity if it's 0. And from here, let's just say by size and keep that at 0.1. So now we won't see anything in the viewport because we have this at 0. But when we go to the volume velocity, that will fill this box full of stuff. Now, actually, I should back up for a second here. We have to specify where this box is. So let's just go like that. Get the whole area. And then it should fill this box with the velocities. So now we go down here, and sure enough, there it is. Okay, so let's go ahead and also take a volume slice, because that's a great way of seeing what's happening. Volume slice, there we go. We're taking those point velocities. Now these point velocities are being extrapolated from a pretty large distance. So if we go to the points here, we have this extrapolation distance of 1. Let's take that down to like 0.05. This is essentially our p-scale on the points. So maybe even 0.1 might be a good value. Yeah, let's do 0.1. So now, looking at what we have here, we have debris vel in X, Y, and Z. The reason why they separate out like that is because traditional volumes don't create vector fields. They just create scalar fields, X, Y, Z. Okay, so if you're used to working with VDBs, you'll see that sometimes it says vector 3 over here. That doesn't exist with regular volumes. But that's what we want to turn this into. So let's start off by converting this over to VDBs. So convert to VDB. Now we have 3 VDB fields. Then we can use a VDB vector merge. And that will create one vector 3 field called debris vel. And take a look at this. Our memory is 11 megabytes. Compare that to 22 megabytes. So we've literally taken this resolution in half just by converting this over to VDBs and turning that into a vector 3 field. So that's pretty cool. We even saved ourselves some memory here by converting this to a vector 3 field. So we're at 11 megabytes versus 17. And so there you go. That is more or less how you would do that. Also, if you're not aware, we have this SOP here called volume trail. And that basically takes points and it takes a velocity volume and it creates streamers which represent the motion of that velocity volume. So in this case, we can just take our original points right here, and that will give us the velocity vectors. So that's really cool. This again, though, is showcasing the volume velocity. We're just taking these points to draw out the streamers. What's cool about this, though, is that now we can take, let's say, our original volume velocity and add a curl noise. So if we go down here, we add a curl noise, we can easily see how we add variation to the velocities on this debris. So we can start breaking this up, and we have a very convenient way of seeing that. So on this curl noise, what you want to do is you want to turn up that scale until you start seeing the colors get around green. So at a scale of 0, we have this. If we have a very low scale, like 0.001, you'll notice that the purple shows where there is velocity, but there's very little velocity there in comparison to the main body, which is the green, right? So if we turn this up until these colors change, that tells us that the curl noise is approaching the same velocity intensity as the points that are moving around. So that preview is pretty cool, but just to be a buzzkill here, we do have 5 million voxels now, and that's not ideal. We do have this mask option right here with the volume velocity, but remember, we're using regular volumes, so we can't just have little areas of density. We have to have, let's say, an entire box of volumes to mask this out with. So unfortunately, even though we have this visualization and this curl noise, it's not the best idea. It's better to just add turbulence when we get to the actual simulation. So turn that off, bring yourself back to 95,000, and this is the best route to go. Okay, so this is one method. Another way is to rasterize the attributes. So we have the trail, we rasterize this, boom. We have, well, velocity once we type that in. But we need to go and tweak this stuff. So let's say particle scale of 0.1 or something like that. What's cool about this, though, is that if we go to our clean SOP and we bring back p-scale, this will respect p-scale. So we do that, and now we take this particle scale back to 1. That is, again, the same p-scale that we simulated this debris with in the first place. Volume slice right here so we can see what we're doing. Now, if we take our voxel size down to 0.05, you can see that this is also giving us a very similar result. However, keep in mind, though, that we're at 429,000 voxels. Down here, we are at, well, 114. So this is 4 times the number of voxels. We can try to play with this minimum filter size, and that'll bring us back down. So that's why this has more, is because of that filter size. You might want to consider just turning that off, honestly. And, you know, we can just kind of play with velocity from here if we want. But it all goes to say that this is not perfect because it's not also going to capture the really small stuff unless you have a filter size going on. So we could see that by just turning this up. So that kind of forces us to get up in this higher count. Whereas this down here just has, for sure, capturing everything, right? So there's pros and cons to each method. In my opinion, the first thing that we did is better because I know for sure that I'm capturing each particle. I'm not relying on the filter size or adding more voxels to do that. And on top of that, I'm already at 114,000. It's a pretty low number. And I could just turn this up if I'd like to. And I'll get more resolution by doing it this way than if I will doing the volume rasterize. So anyway, that is a bunch of stuff to think about. In the next video, let's throw this in the sim and talk about a few other settings.